Welcome to Engten Precalculus for Engineering. For this video, we are going to talk about Module 1.2, Integer Exponents. Our outline: first, we'll talk about theorems on integer exponents, and later on we will talk about zero and negative integer exponents. This is just a brief lesson and maybe just review for some of you. So let's get over it. So let me talk about the basic of exponent. In general, if a is a real number and n is a positive integer, a raised to n is equal to a times a times a times a. There are n factors of a. This means we need to multiply a n times. N is called the exponent. A is called the base, and a raised to n is called the nth power of a. Using the definitions stated above, we are going to answer these problems. For part 1, we have 2 raised to 5. 2 is the base, 5 is the exponent. So to answer this one, we need to multiply 2 by itself 5 times. That is 2 times 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8, times 2 is 16, times 2 is 32. Therefore, 2 raised to 5 is equal to 32. For part B, negative 1/2 is the base, 3 is the exponent. In this case, this is equal to negative 1/2 times negative 1/2 times negative 1/2. We need to multiply negative 1/2 by itself 3 times. Okay? So negative 1/2 times negative 1/2 is positive 1/4. Positive 1/4 multiplied by another negative 1/2 is negative 1/8. For part C, we have negative 3 raised to 4. And then for part D, we have negative 3 raised to 4. Okay, if you take a look at the two problems, seems like they are the same, but they are not. For part C, the negative is included in the base. For part D, the negative is not part of the base. Okay, only the 3. Okay, so in this case, for part C, we need to multiply negative 3 by itself 4 times. So that's negative 3 times negative 3 times negative 3 times negative 3, which is equal to positive 81. Okay, so positive 81. For part D, this negative sign is not included in the base, so the negative sign should be outside, and then we need to multiply 3 by itself 4 times. In this case, the answer is negative of 3 times 3 times 3 times 3, which is 81. So our next task is to simplify expressions involving integer exponents. And to do this, there are theorems that we need to apply. The first theorem states that if n and m are positive integers and a is a real number, then a raised to n multiplied by a raised to m is equal to a raised to n plus m. If you take a look at this one, these two factors multiplied together have the same base. Okay, in this case, their base is a. Okay, the only difference about them is their exponents. The first one has an exponent of n. The second one has an exponent of m. If we multiply them together, what do we need to do? We just need to copy the base, but we need to add their exponents, n plus m. Okay. Theorem 2, on the other hand, states that if n and m are positive integers and a is a real number, then a raised to n and then raised to another exponent m is equal to a raised to n m. This means that if an exponential expression is raised to another exponent, we just need to multiply these exponents together. Theorem 3. If n is a positive integer and a and b are real numbers, then the quantity of ab raised to n is equal to a raised to n times b raised to n. This is called the exponent of a product. If you take a look at this one, a and b, a times b is the base. Okay, the base has two factors, a and b. If this is the case, we need to distribute the exponent n to each of the factors. So a raised to n times b raised to n. Theorem 4 states that if n and m are positive integers and a is a real number where a is not equal to 0, then a raised to n divided by a raised to m is equal to a raised to n minus m. Okay, so if you remember right, in Theorem 1, when we are multiplying these two expressions together, we need to add their exponents, right? But in this case, in Theorem 4, if we are dividing these two expressions together, we need to subtract their exponents. Alright. And lastly, for Theorem 5, if n is a positive integer and a and b are real numbers where a over b is not equal to 0, then the quantity a over b raised to n is equal to a raised to n over b raised to n. This is the same as theorem number 3, right? It's just that this one is a quotient. Okay, so a, we need to distribute the exponent n to both to the numerator and the denominator. So we have a raised to n all over b. And then for the last part of our discussion, how do we deal with exponents such as 0 or negative integer exponents? Okay, there are rules, right, for these kinds of expressions. If n is a positive integer and a is a real number where a, of course, is not equal to 0, then a raised to 0 is equal to 1. This is the rule for 0 exponent. Whatever the base, alright? So we do not mind the base. If the exponent is 0, the whole expression is equal to 1. On the other hand, if we have a negative exponent, say a raised to negative n, to simplify a negative exponent, of course, we need to transform these negative exponents into positive exponents. Alright, so if an expression contains a negative exponent, it is not simplified yet. So we need to transform those expressions with negative exponents into expressions with positive ones. So we can do that by using this rule. Okay, if we have a raised to negative n, we just need to get the reciprocal of whatever that expression, say 1 all over a. Now the exponent becomes positive. In the following slides, we are going to answer some problems that involves these different rules and theorems. For the first example, we are going to multiply the two expressions. The first expression is 4x raised to 4, y raised to 3. And the second expression is negative 5x raised to 5, y squared. How do we multiply expressions like this? And what theorem do we need to apply in this one? First, each of these two expressions have constants, right? The first one has 4, the second one has negative 5. And to simplify, to multiply these two expressions, the first thing that we need to do is, of course, to multiply the two constants together. So we have 4 times negative 5. Secondly, we can only combine those variables with the same base. In this case, we will combine x raised to 4 and x raised to 5. Remember, the operation here is multiplication. So we need to multiply the two. X raised to 4 multiplied by x raised to 5. And lastly, we need to multiply y raised to 3 and y raised to 2. Okay? So, what is 4 times negative 5? That's negative 20. What's x raised to 4 times x raised to 5? If you remember the theorems that we have discussed, this is an example of theorem number 1, right? The bases of these two expressions are the same, x and x. So what do we need to do? We just need to add their exponents together. So this one becomes x raised to 4 plus 5 is equal to 9. So that becomes x raised to 9. And finally, y raised to 3 times y raised to 2 is y raised to 3 plus 2 is 5. So that is the answer for the operations being asked. Our next example is the same as our previous example. Okay, so in this case, we are multiplying 4n x raised to 5n and 5n x raised to 4n. So we need to multiply the constants together, right? So 4 times 5 and then n and n, so that's n times n, and then finally x raised to 5n multiplied by x raised to 4n. Simplifying, 4 times 5 is 20, n times n is, what do you think is the exponent here? Okay, so there is an invisible exponent 1 for this one. Okay, remember your high school math, we don't need to write one exponent. So if it's a variable, it's understood that there is an exponent 1 over there, right? So what is n times n? We need to multiply the exponents together, that becomes n squared. Okay, and then x raised to 5n times x raised to 4n, we need to add the exponents together. So 5n plus 4n is 9n. Therefore, the product is 20n squared x raised to 9n. Okay, another example. We need to simplify these three expressions. Okay, the first one, we have n squared raised to another exponent 2. Okay, so this is actually an example of theorem number 2, right? So what do we need to do here? We need to multiply the exponents together. So that's 2 times 2. Okay, so this becomes n raised to 4. For the second one, we need to multiply 2 times n. What's 2 times n? That's 2n. Okay, so this becomes x raised to 2n. For the last one, we need to multiply n and n times n. What's n times n? N times n, this is actually theorem number 1, right? N raised to 1 multiplied by another n raised to 1 is n raised to 2, or n squared. This example is a little bit the same with the first one, only this time we are multiplying 3 expressions together. But the principle is the same. First, we need to multiply all the constants first. So that's negative 5 times negative 6 times, if you take a look at the third expression, there is no number, right, before the variables. Okay, but there is an invisible 1 right here. Okay, there is a 1, so times negative 1. Okay, and then r, we have r cubed for the first expression. We do not have any r in the second expression, but we have r squared in the third expression, so multiplied by r squared. And the next s, so s raised to 4, and then in the second expression is s raised to 5, and in the third expression is s. And lastly, t, we have t squared multiplied by t raised to 4, and then we do not have any t in the last expression. And now we perform the operation. Negative 5 times negative 6 is positive 30, times negative 1 is negative 30. R raised to 3 times R raised to 2 is R raised to 5. S raised to 4 times S raised to 5 times S is S raised to 10. T raised to 2 times T raised to 4 is T raised to 6. Therefore, our answer is negative 30, R raised to 5, S raised to 10, T raised to 6. This example is an application of the third theorem, right? So the power of a product. Okay, so if you recall, this expression here, 2x cubed y squared z, they are all raised to 3 because of the presence of parentheses here. Alright, so to simplify this one, this expression right here, we need to distribute this exponent to each of the factors right here. Okay, so we need to distribute the exponent. So that becomes 2 raised to 3 multiplied by x raised to 3 raised to 3, then multiplied by y raised to 2 raised to 3 times z raised to 3. Okay, so using the same theorem, we are going to do that in here as well for the second expression. Remember, this one has a constant of 1. So when we have negative 1 here, so negative 1 raised to 4, and then x squared raised to 4, and then y raised to 3 raised to 4, and then z raised to 4 raised to 4. Okay, to simplify this one, we need to evaluate each of these variables. 2 raised to 3 is 2 times 2 times 2, that's 8. X raised to 3 raised to 3 is x raised to 9 because we need to multiply the exponents together. Y raised to 2 raised to 3 is y raised to 6, and then z raised to 3. Okay? For the second expression, negative 1 raised to 4 becomes positive 1. We don't need to write positive 1 anymore. X squared raised to 4 is x raised to 8. Y raised to 3 raised to 4 is y raised to 12. Z raised to 4 raised to 4 is z raised to 16. Alright. Then we can multiply now the two expressions together. So 8 times 1 is 8. X raised to 9 times x raised to 8 is x raised to 17 because we need to add their exponents together. Y raised to 6 times y raised to 12 is y raised to 18. Z raised to 3 times z raised to 16 is z raised to 19. Therefore, the answer for this problem is 8, x raised to 17, y raised to 18, z raised to 19. We are given the problem 8a raised to 5b raised to 2 all over 2a raised to 3b raised to 8. So for this one, we are going to apply theorem number 4. Okay, what does theorem number 4 state? It states that when we are given two expressions together, we need to subtract their exponents, right? In this case, 8 can be expressed as 2 raised to 3, but actually we can separate each of these variables. Okay, we can separate the constants together, and then we need to separate those a's. So a raised to 3, or a raised to 5, and then over a raised to 3, and then we have b raised to 2 all over b raised to 8, and then we can actually simplify this one now. 8 divided by 2 is 4. A raised to 5 divided by a raised to 3, we need to subtract their exponent. So that becomes a raised to 5 minus 3. The same is true here. B raised to 2 minus 8. Okay, so and then we simplify. So this becomes 4a squared b. This is negative 6. Okay, this is not yet simplified because of the presence of the negative exponent. So what do we need to do with this negative exponent? We need to get the reciprocal. This means that this part of the expression will be transferred to the denominator. Okay, so we have 4a squared all over b raised to 6. You see, the negative exponent from here, when written in the denominator, is now a positive exponent. So our answer for the problem is 4a squared all over b raised to 6. Using the same principle from the previous example, we are going to answer this one. Okay, so we need to separate each of the variables with the same base together. So n over n, and then we have x raised to 6n all over x raised to 3n. Okay, so 6 divided by 3 is 2. N all over n, so we have n raised to 1 minus 1, and then x raised to 6n minus 3n. So this becomes 2n raised to 0 x raised to 3n. Okay, but since we know that anything that is raised to 0 is equal to 1, this becomes 2 times 1 times x raised to 3n. Okay, so n raised to 0 is now written as 1 because that is the rule for the 0 exponent. So 2 times 1 is 2 x raised to 3n. So the answer is 2x raised to 3. For our final example in module 1.2, we are going to answer this expression. And this is actually now a combination of some of the theorems we have discussed. Okay, so we have x raised to negative 3, y raised to 4, z raised to negative 5, all over x raised to 6, y raised to negative 2, z raised to negative 4, and this whole expression is raised to negative 2. Okay, actually, there is no single way to solve expressions or simplify expressions something like this. Alright, so we can actually solve this one by simplifying what is inside the parentheses first, and then whatever is the simplified form of this one in the parentheses, we raise to negative 2. Or what we can do, we can also distribute this exponent, negative 2, to all the terms or all the variables in the numerator as well as in the denominator. Okay, because there is theorem 3 and theorem 5 supporting that one. Okay, so there is no single way to solve problems something like this one. So whatever is convenient to you, whatever you know, you can actually use it. Alright, so how do we solve this one? Okay, I prefer simplifying what is inside the parentheses first. So since we have x, y, and z as the variables, now we have x raised to negative 3 minus 6 because the exponents need to be subtracted. Okay, and then y raised to 4 minus, in the denominator is negative 2, so that's 4 minus negative 2. and then z raised to negative 5 minus negative 4. Okay, and then all of these is raised to negative 2. Okay, simplifying further, we have x raised to negative 3 minus 6 is negative 9. And then y, 4 minus negative 2 is positive 6. And then z, negative 5 minus negative 4 is negative 1. And then everything is raised to negative 2. Okay, now we can write these variables with negative exponent, x raised to negative 9 and z raised to negative 1 in the denominator. First, you can do that, right? And what you can also do is to distribute this exponent negative 2 to each of the variables. So we will do that here. Okay, so we have x raised to negative 9 raised to negative 2, y raised to 6 raised to negative 2, z raised to negative 1 raised to negative 2. Okay, so if we simplify this one, this becomes x raised to positive 18, y raised to negative 12, z raised to positive 2. And we know that this negative exponent can be written in the denominator. Therefore, this becomes x raised to 18, z raised to 2 divided by y raised to 12. Okay, so that's our final answer for this one. X raised to 18, z raised to 2, y raised